Hello students, welcome back. Let's go to section 3 of this notebook, the matrix exponential. As I wrote here, this is a review. We covered the very same topic in lesson 13a. So if you just went through lesson 13a and if you feel comfortable with this topic, the matrix exponential, you can skip here because this is going to be the very same review mostly. But then again, there must be some student who skipped lesson 13, both 13a and b, and trying to connect what they learned in pre-calculus about matrices directly to lesson 14. In that case, this is an absolute must because in pre-calculus or even in linear algebra, we don't usually deal with matrix exponential. This is a new topic here. And here is a definition of the matrix exponential. Please compare this definition with a real number case here, real exponential function, given by the Taylor-Maclaurin series expansion. And this is an extension to complex function. Replace x by z complex number, then that's a complex case. And replace x by a square matrix, then this is a matrix exponential. Because A is a square matrix, A times A cubed, a to the fourth power, all those are valid computations. So this is well defined. And as for the convergence here, well, I regret erasing these. This one always converges. The interval converges is negative infinity to positive infinity. This too always converges as well. It turns out that radius of convergence is infinity. Likewise, you don't really have to worry about that here either. Now, this may be the definition, but this is not the most useful form. This one is. Replace A by a scalar multiplication A times T. A times T or T times A, it doesn't matter. If you have two matrices, A times B is not equal to B times A in general, but this is scalar multiplication, so A times T, T times A, that makes no difference. And replace A by A times T, then this A times T to the k power, so by the exponential we get that. And replace A by A times T here, and A times T squared, A times T cubed, A times T fourth power, and so on and so forth. And we have this expression actually generated from the definition. Turns out this is going to be a little bit more useful as far as lesson 14 is concerned. Okay, all right. Now that we considered the definition of the matrix exponential for all square matrices, let's consider some examples, and let's begin with the simplest possible case. When the matrix is a diagonal matrix, that's the simplest case. It turns out that the matrix exponential of a diagonal matrix is a diagonal matrix given by exponential of the diagonal entries. So if you have all those lambdas in this principal diagonal, you just have e to the lambda powers there. Special case, if we start from d times t, then multiplying by t, the scalar multiplication, will not change anything in all these zeros because 0 times t is still 0. The only change takes place from the principal diagonal where we have lambda times t. So if you apply the same idea here, exponential of the diagonal entries, then you're going to get this, e to the lambda t power. So, if I know this, then this one follows immediately. So let's prove this. How do I do that? Let's begin with some brute force computation. Here's d squared, d times d. This is d, and that's another d. Let's multiply. First row times first column. We have lambda 1 times lambda 1, so that's lambda 1 squared. And everything else here, they're all 0 times 0. Adding a bunch of zeros do not change anything, so we have just lambda 1 squared. How about the next entry? First row times second column. This one gives you 0 times lambda 1, that kills off. And this 0 kills off this lambda 2, 0 times lambda 2. And everything else here and there they're all 0 times 0. So all 0, you get 0. And then you repeat the same thing for the third, fourth, and how about the last column here? First row times last column, again the same deal. This 0 kills off this lambda 1, and this 0 kills off this lambda n, and everything else in the middle, 0 times 0, so we have to have 0. All these must be zeros. And then if you use the same idea in the second row, this is what you're going to get. You're going to just lambda 2 squared here, and so on and so forth. And then what do you have? We have just lambda to the second power, just second power in the principal diagonal, and everything else is 0. Repeat the same argument here, then you're going to get third power, and then fourth power, and so on and so forth. And here's the general case. Begin with k minus first power, and do the same thing, same matrix multiplication carefully, and you're going to get lambda to the k power there. Does it help? Oh yes, it does. Please recall that the definition of the matrix exponential is like this, and it is given by power series of a to the k power, so we need d to the k power there. And then we found out d to the k power works like this, so we can rewrite everything. Here's a definition, and d to the k power like this. Now we have this scalar multiplication, the coefficient 1 over k factorial. You can multiply that to each entry, but all these zeros make no difference, so the scalar multiplication will apply only to principal diagonal. So we have this 1 over k factorial times lambda to the k power. And also, if I add them all up, what happens? All the other entries, we have a bunch of zeros added, so no change. So all the addition will take place only on the principal diagonal here. So what do we have? We have Taylor-Maclaurin series expansion here, and then here, and so on and so forth. So you have to have exponential e to the lambda power. So that completes the proof. The conclusion, let's go back again. If you have a diagonal matrix, then the matrix exponential is a diagonal matrix given by exponential of the eigenvalues. Now let's consider even simpler case. What if d is equal to 0? Zero matrix, then all these lambdas are all zeros. So we have e to the 0 power here all the way. And what is e to the 0 power? What is e to the 0 power? And it's 1. So we get this conclusion. All those ones in the principal diagonal, everything else is 0, so this is the identity matrix. So the conclusion is e to the 0 power is equal to I. And please make this connection. E to the 0 power is 1 for the real number arithmetic. And this is the corresponding identity for matrix multiplication, matrix exponential. Okay, that was the simplest case, and then here are some more rules. And this one we just talked about. Now here's rather difficult rule, to tell the truth. This is the exponent rule. E to the a plus b power is equal to e to the a power times e to the b power. But I'm afraid this is not always true. It is true when a and b commute. A times b is equal to b times a, and this commutativity was always true for real number arithmetic. So for real number exponent rules, you didn't really have to worry about any conditions. But for matrices, yes you do. When a pair of matrices A and B commute, then yes, you can use this matrix, the matrix version of the exponent rule. Yes, you can use that. If they do not commute, then no. And this rule will be quite useful in lesson 15 when we solve some systems of first order linear systems, systems of first order linear equation, linear ODEs with variable coefficient matrix. Excuse me. Let me not talk too much about lesson 15, and let's go to the next rule here. Turns out e to the a power is always invertible, and it turns out the inverse is e to the negative a power. So a may or may not be invertible, but e to the a power is always invertible, and it turns out the inverse is e to the negative a power. Why is that? From here, put b equal to negative a, then let's make this observation here. A times negative a is equal to negative a times a, and that is negative a to the second power. Because what is negative a? It is negative 1 times a, so scalar multiplication, I can always pull it out, and what's left is a squared. So they commute. A and negative a commute. So we can use this rule here. So basically, e to the a power times e to the negative a power is equal to e to the a power plus negative a, so minus a. That's equal to e to the 0 matrix, and what is this? Oh, wait a minute, it's over here. Sorry about that. That's I, the identity matrix here. So what do we have? This matrix times that matrix is the identity, so they're inverse of each other. So there you go. Now, one more warning here. A may or may not be invertible. A inverse may not exist, but e to the a power is always invertible, and the inverse is e to the negative a. The first rule here and the third rule here will be quite useful for lesson 14. This one, on the other hand, we're not going to use this very often in lesson 14. Yes, we just used it here to deduce this result, but otherwise this is not that useful. In lesson 15, we do use it. As for why this is true, well, I have a proof here that's related to the binomial expansion formula, but I'm going to leave this detail to the students. And if you want a little bit further explication about this, well, you can always review the lesson 1a, where I proved something similar. As a matter of fact, exactly the same thing for real number arithmetic. Here, let's just move on, and let's just move on to example problems. Okay, here's a problem. Find the matrix exponential e to the at power for this 2 by 2 matrix. What is e to the at power? Well, this is the definition of exponential, and a is at power. Instead of a, we have at power, like this. Then you're going to get this expression. So let's copy and paste this thing over there. And then let's try to work this one out for this. Okay, all right. Oh, I already have it here. Okay, so our goal is to calculate this quantity where t is a scalar. All right, so far so good. So if I find all these, at, a squared, t squared, a cubed, t cubed, and so on, and then add them up, then I'm going to get what I want. So let's calculate those, and oh boy, those are, what can I say, some unpleasant computations. It'll turn out like this. So 0 power is always I, that's the definition. Okay, so I is 1001, and a to the first power is just a, so far so good. So a times t, multiply by t, so multiply by t here, so there you go. T times 0 doesn't change anything, so principal diagonal stays at 0. Now this is a squared, a times a, and you're going to end up with this matrix multiplication. And then what do you have? A squared t squared turns out like this. Make sense? Okay, now that we got a squared, and this is a squared times a, do some further computation. It turns out like this. This is a to the third power. So multiply by t cubed, we get that. One more time. This is a to the third power, and then multiply a again, and we ended up with the identity matrix. Multiply by t to the fourth power, we get this matrix here. But then again, this identity is important because from this point on, multiply by a, then we get a again. Multiply by a again, then we have a squared, and then a cubed. We have the cycle continuing. So we have this kind of pattern. And in the end, the definition here, given by all these matrices there, will turn out to be like this. Let's see. Focus upon 1, 1 entry. Okay. 1 and then t to the 0 power. Next, 0 and then t to the first power. Next, negative t squared, but we need 2 factorial downstairs because of this. And then 0 t to the third power, and next one will be t to the fourth power over 4 factorial because we need 4 factorial. And then we're going to get 0 again, and so on and so forth. So what do we have here? We have alternating sign, and then all those even powers are all zeros. No, excuse me, all the odd powers are 0. Alternating sign for even, we have cosine of t. And the other computations, again, you have to be really careful about pluses and minuses and all those kind of things. And the rigorous testing can be rather tedious. But if you do it right, you're going to get this. Cosine of t, sine of t, negative sine of t, cosine of t. So basically what we get is alternating sign, plus minus, plus minus, plus minus, and then alternating zeros. So we get all the even powers only, odd powers only, kind of like that. So this is e to the at power. So matrix exponential turned out to be something very simple in this case. Do you have time for another problem? Okay, let's go. Another problem. Recall our basic goal. Again, we want to calculate this kind of matrix exponential. Okay, Taylor-Maclaurin series. So you need to calculate b, b squared, b cubed, and so on and so forth. And here we go. B to the 0 power is I, like that, okay. And then this is b, so b times t is like this. And multiplying by t, we have, well, this form. But please pay particular attention to that blue term, this 1, 2 entry, which is highlighted in blue. And then this is b squared. B times b, and it turns out, everything stays the same. This is 2. That's interesting. And then multiply by t squared. Okay, everything stays the same. T squared, 0, but this one is 2 t squared. Are we going somewhere? Let's see. B cubed, so b squared times b, and do your matrix computation carefully, and you're going to get 3 here. We are really getting somewhere. B to the fourth power, third power times this, and if you calculate, you're going to get 4 here. And then you're going to get 5 here. Repeat it inductively, you're going to get k there. I'll leave the details to the students. It's not really a fun computation to do, but you'll be able to find out the pattern if you slow down and try not to make any mistake. So multiplying by t, t squared, t cubed, and so on, we get all these. And then put all those into Taylor-Maclaurin series expansion. Here, there, the same t, so we have usual e to the t power. But this one here, we have actually the derivative. Because if you take the derivative, 2 comes out, 3 comes out, 4 comes out, kind of like that. So it'll turn out t e to the t power. A bit tricky to see the derivative here, but it'll turn out like that. The detail is left to the students. Okay, we went through a couple of examples that required a lot of tedious and unpleasant computation, but in the end, we were able to calculate the matrix exponential, e to the at power and e to the bt power. That's where we are going to stop.